Hi, my name is Shahroz Ahmed, and in this video I'm going to discuss the topic on circular motion. It's a topic of IP physics. So let's start off with circular motion. So circular motion is basically it is the motion of an object in a circle. So let's suppose we have an object, that is we have a circle with center, and there's an object that is revolving in circles on this circle. So we have to discuss some different terms when the object revolves around a circle. So the first term that we have to discuss is the period, or we can say the time period. So I'll write it over here. Period or time period, it's the same thing. So it is basically, by definition, it is the time taken by an object to complete one revolution. It is the time taken by the object to complete one revolution. That is called a time period, and we represent the time period in seconds. So second is the unit for the period or time period. And in one revolution, if we talk about the angle in a circle, it unlike one revolution is equal to 360 degrees, or if we talk about in the angle in radians, so that will be 2 pi radians. So that will be the time period, the time taken by an object to complete one revolution. Now the next thing that we have to discuss is the frequency. Alright, so for frequency, let me just draw a circle and then I'll explain you how we can define a frequency. So let's suppose we have a circle with a center. An object is revolving in a circle like this. Now the number of revolutions that this object will cover in 1 second will be called the frequency of that moving object. I write it over here. The number of revolutions done by the object in a circle is considered to be its frequency. Now frequency is basically equal to 1 over time period, and the unit of frequency is hertz. Alright, now we can I can discuss the angular frequency. So angular frequency is basically represented by omega, and this omega is equal to, this is represented for angular frequency, and this omega is equal to 2 pi f, or we can say the angular frequency can be equal to 2 pi over capital T. So this is the angular frequency of the object that moves in a circle. Alright, so after this angular frequency we will discuss about the angular displacement. Alright, so angular displacement. So for the angular displacement, I again have to draw a circle. So let's suppose here we have a circle with a center. An object is on point A on the circle, and after some time the object has moved to point B on the circle. Now while moving from point A to point B, the angle that the object has formed at the center of the circle, this angle will be considered as the angular displacement. So by definition I can write it as the angle subtended at the center of circle at the center of a circle when an object moves from point A to point B on the circle, and we represent this angle in radians. So the unit of this angle, the unit of angular displacement is radian, and we represent it with RAD. So this is the definition for the angular displacement. Now after this one we have to discuss about the angular velocity, so let's move on to that. Alright, so let's discuss the angular velocity. So this is the circle with a center, and an object moved from point A to point B, and it formed an angle at the center that was theta, and I said that theta is the angular displacement. Now the angular velocity will be the rate of change of angular displacement. So the rate of change of angular displacement will be considered as the angular velocity. So we represent angular velocity with omega, that is equal to delta theta by delta t, where delta theta is the angular displacement and delta t is the time. So the unit for omega will become radians per second, where the unit for theta is radians. So this is how we represent the angular velocity. Now the next thing that we have to discuss is the angular acceleration. So for the angular acceleration we can say the rate of change of angular velocity is angular acceleration. The rate of change of angular velocity is angular acceleration. We represent angular acceleration with this symbol. This is called alpha, and it is equal to delta omega by delta t, and the unit for angular acceleration is radians per second square. So this is the definition for the angular acceleration. Now we will see the relationship between the linear velocity, like the uniform linear velocity, and the angular velocity. So let's discuss that. Alright, so the relationship between the linear velocity and the angular velocity is this one, that linear velocity is equal to radius times the angular velocity, or we can say it's v equals to r omega. This is the relationship between the linear velocity and the angular velocity, where omega is the angular velocity, its unit is radians per second, and this is the radius of the circle, and this v is basically the linear velocity whose unit is meters per second. So this is the relationship between the linear velocity and the angular velocity. Alright, so now similarly we will see the relationship between the linear and angular acceleration. So the linear acceleration is represented by a, and that is equal to r alpha, where alpha is the angular acceleration, r is the radius of the circle, and a is the linear acceleration. So this is the relationship between the angular acceleration and the linear acceleration. So you can remember these two relationships, v equals to r omega and a equals to r alpha. Now after this angular acceleration we have to discuss the concept of centripetal acceleration. So for the centripetal acceleration, let me just erase it. Alright, so let's discuss the concept of the centripetal acceleration. For that purpose, just suppose that we have a circle with a center, and an object is at point A over here. It moved from point A to point B in some time, and the angle subtended at the center of the circle is very small. So let's suppose it's delta theta, and the time that it took in order to move from A to B, that is delta t, and this distance from A to B is so small that it will look just like a straight line. So we can just represent this one as a straight line, because I have told you that this angle is very small. So this distance from A to B will just seem to be a straight line instead of a circular line. Alright, so in order to find out the distance for this line, we have the time, and we have the speed by which the object is moving. That speed is v. So we can say that the distance from A to B will be equal to, by using the formula of distance is equal to speed multiplied by time. Speed is v and time is delta t. So we can say that this distance will be v delta t. So remember that this distance from A to B is v delta t. Now let me just draw this circle again. So I'll draw it here. This is the center, this is point A, and over here we have point B. Now when the object was moving at point A, the angle subtended at the center is delta theta. So when the object was moving at point A, the velocity of this object was tangent to point A. So we can say the velocity of this object at this instant was like this. We'll call it as VA. And the velocity of the object at point B will be in this direction. We'll call it as VB. Now the change in velocity we can work out. So the change in velocity we will work out by using the vector. So VA is over here. This is VA. And I'll put VB over here on the head of the VA. This is VB. Now the change in velocity is this much. This will be the change in velocity, delta V. Alright, so this will be delta V. Now you see this angle is delta theta. So when the object moves from A to B, the angle subtended at the center will be delta theta. Similarly, the angle over here will be equal to delta theta. Now we'll use the concept of the similar figures on these two triangles. So I'll draw these two triangles over here. So this is my first triangle. This is the first triangle where the angle delta theta is over here. This is R, and over here we have V delta t. Now this is my second triangle. Now I'll use the concept of similar triangles, and I'll write down an expression over here. So from that expression I'll find out the centripetal acceleration. So look over here, this is delta theta. The side opposite to delta theta is V delta t, and the side adjacent to delta theta is R. So I'll write it as opposite over adjacent. So it will be like V delta t divided by R equals to, now come on to this triangle. So this is delta theta. The side opposite to delta theta is delta V. So I'll write delta V over here. And the side adjacent to delta theta, this is VA or VB. I'll consider them as only V. So it will be like delta V over V. Now from here I'll do some rearrangement. So I'll move this delta t over here, and I'll move this V over there in the numerator on the left side. So it'll become V times V over R equals to delta V over delta t. Now V times V over R is V square over R equals to, now delta V by delta t, by definition, as we know that the rate of change of velocity is the acceleration. So this velocity will be considered as the acceleration will be considered as the acceleration in the circle. That will be called the centripetal acceleration. So we'll call it as the centripetal acceleration. That will be equal to V square over R. Now let's talk about the direction of the centripetal acceleration. So the direction of the centripetal acceleration will always be perpendicular to the direction of the tangential velocity. So as you can see in this figure, the velocity is in this direction. So the direction of the acceleration will be perpendicular to this one, that will be in this direction, so it will always be towards the center of the circle. So I'll write it here. The direction of centripetal acceleration, I'll just write AC, is always towards the center of the circle. Towards the center of the circle. So this will be my centripetal acceleration. Now the next thing that we have to discuss is the centripetal force. So let me just erase it. Alright, so let me just first of all write down the definition for the centripetal force. So the force that keeps the object moving in a circle is centripetal force. So this is the definition. The force that keeps object to move in a circular direction is called the centripetal force. For example, we have an object that is moving in a circular path. Now the continuous force that is being acting on this object that is keeping it in the circular path is the centripetal force. Okay, now let's come on to the formula. So as we know that force is equal to, according to Newton's second law, we know that the force is equal to mass times acceleration. Now if this is the centripetal force, so I'll put C in the subscript of F, so it'll be like centripetal force equals to mass times centripetal acceleration. So the centripetal force, and as we have just derived that the centripetal acceleration is v square over r, so we can say that our centripetal force will become equal to mv square over r. So this will be the formula for the centripetal force. And as we know that because it's a force, so the unit of this force will be Newton. Now one more thing, let's write down this centripetal force in terms of the angular velocity. So till now I have just written it in the form of the linear velocity. So the linear velocity is equal to r omega, so I'll just insert r omega in place of v over here. So my centripetal force will become equal to m r omega whole square over r, so it'll become m r square omega square over r, so that will get cancelled. So my centripetal force will become equal to m r omega square, and omega will be the angular velocity, m is the mass of the object that is moving in the circular path. Let's suppose this is the object, so m will be the mass of this object, and r will be the distance from the center of the circle. So this is the force that keeps the object in moving a circular path, and here we have just derived their formulas. So this is it for the topic of the circular motion, and now we will do some of the exam related questions. Alright, so here we have a question that says mass m is attached to one end of the string. The string is passed through a hollow tube and mass m is attached to the other end. Friction between the tube and the string is negligible. Mass m travels at a constant speed v in a horizontal circle of radius r. What is the mass m? So we have to work out this mass m. Now you see this object is moving in a circular direction, so the centripetal force is being acting on this mass, and the cause of that centripetal force is this, the weight due to this mass. So what we do is we'll put the weight of this mass equals to the centripetal force, and from there we'll make m as our subject. So the weight is the cause of the centripetal force, so I'll say that weight is equal to the centripetal force. Now the weight is capital mg and the centripetal force is mv square over r. Now the capital M will be equal to mv square over gr. So let's see the option, it's here, so it's option D, mv square over gr. Alright, so here we have another question related to the circular motion. It says two satellites W and X have the same mass. They have circular orbits around the same planet. W is closer to the surface than X. So what quantity is smaller for W than for X? So let's suppose this is the planet, and W is closer, so let's suppose this is W, and X is farther, so let's suppose this is X. They are revolving around this planet in the circular path, so let me just draw the orbit, the circular orbit. Then for X, this is the circular orbit. Alright, so W is closer to the planet, X is far from the planet. So let's see the option 1. It says gravitational force from the planet. Which quantity is smaller for W? So smaller, we have to see the smaller W, because W is closer to the planet, so W will have more gravitational force as compared to X, because force is F equals to G M over R square. So the force is inversely proportional to the square of the distance. So X is at more distance, so the force on X will be lesser as compared to W. So W have more gravitational force. Let's see the angular velocity. So angular velocity is omega equals to, basically the formula is V equals to R omega. So omega is equal to V over R. Still, omega is inversely proportional to R, so the X has more radius as compared to W, so X will have more angular velocity than W. Sorry, X will have less angular velocity than W. W will have more angular velocity. Now let's see the orbital speed. So orbital speed is V equals to R omega. So orbital speed is directly proportional to the radius. So the radius of W is less than the radius of X. So the orbital speed for W will be less than the orbital speed for the X, so it will be option C. But still, let's see the option D. So option D is orbital period. Orbital, basically period, they are moving with the same speed. So it means that it will take more time for X to complete one orbit, and it takes less time for W to complete one orbit. Alright, so this is not the orbital speed, because orbital speed for let's do it once again. So question number 30, it says two satellites W and X have the same mass. They have circular orbits around the same planet. W is closer to the surface than X. What quantity is smaller for W than for X? So for this question, let's draw the figure first. So this is the planet, W is over here, this is the orbit of W, and this is the orbit of X. This is W over here, this is X over here. X is away from the center of the planet. Now let's see the first of all, it says gravitational force. So as we know that force is inversely proportional to the square of radius. So more radius, less force, less radius, more force. So the radius of W is lesser than X, so it will experience more force. So this cannot be the option. Next one, it's angular velocity. So angular velocity is basically, the formula is omega equals to V over R. So it's basically inversely proportional to the radius. So more radius, less angular velocity, less radius, more angular velocity. So in this case, W will have more angular velocity. So this cannot be the option as well. Now let's see option C. It says orbital speed. So orbital speed, so it's like V equals to R omega, or we can say V is directly proportional to R. More radius, more speed, less radius, less speed. So X has more radius, it will have more speed. W has less radius, it will have less orbital speed. But let's see option D as well. So orbital period. So orbital period is basically directly proportional to R to the power of 3/2. Okay, so let's assume for this one it has more radius, so it will have more time period. This W will have less radius, so it will have lesser time period. So because the power of this R is 1, the power of this R is 1.5, like 3/2 is equal to 1.5. So orbital period is more significant than the orbital speed, so we'll take option D as our correct option. If we do not have the option of orbital speed or orbital period, then we would have taken the option of orbital speed. But in this case, we will take the option of orbital period. Alright, let's do the next question. It says P and S are 2 points on a gravitational equipotential surface around a planet. Q and R are 2 points on a different gravitational equipotential surface at a greater distance from the planet. The greatest work done by the gravitational force is when moving a mass from. Alright, so let's discuss the equipotential surfaces. So P and S, they are on the same orbit. It means the potential, the gravitational potential of P is equal to the gravitational potential of S. And the Q and R, they are also on the same orbit. So the gravitational potential of Q is equal to the gravitational potential of R. So if we move S to P or P to S, there will be no work done because the potential is not changing. If we move R to Q or Q to R, still there will be no work done. But if we move R towards S, then there will be some work done by the gravity. But if we move S to R, then we will do the work done against the gravity. The gravity will not do the work done, but we will do the work done. Now let's see the options here. So the first option, it says the greatest work done by the gravitational force is when, let me just scroll it a bit, let me just zoom it out. Alright, so it says the greatest work done by the gravitational force is when moving a mass from P to S. So because as I told you, P and S, they are on the same equipotential surface, so no work will be done. Q to R, they are also on the same equipotential surface, no work will be done. R to P, so if we move from R to P, so we are moving towards the gravitational field, so there is some work done that is done by the planet, so this will be our option C. Now let's see S to R. Now S to R, so over here this is not the work done that is done by the planet, but this work done is being done by some external force, by some external energy. So S to R will not be the correct option. So the correct option will be R to P. So this is it for this topic for the circular motion. Thank you.